Hi everyone. This is a short lecture on section 2.3, which is characterizations of invertible matrices. In section 2.2, we prove the following. Right, and the theorem was an n by n matrix A has an inverse matrix if and only if A row reduces to In. Furthermore, in this case, when A inverse exists, A inverse is equal to E1, E2, EM, where the EIs are the elementary matrices corresponding to the row operations which reduce EI to the identity. Or reduce A to the identity. So that is one very succinct way of saying when a matrix has an inverse. Okay. Section 2.3 has a much more involved theorem. And section 2.3 is more just a summary of like everything we've gone over in chapter 1 and chapter 2 and just puts it all into one space. Okay, and the statement of that theorem is as follows. So an n by n matrix A has an inverse if and only if any of the following are satisfied. Any of the following are satisfied. So it has an inverse if and only if any one of the following are satisfied, if and only if all of the following are satisfied. Okay, so the following statements, they're all equivalent. They all mean an inverse exists. All right, so let's see, I don't think I have enough space to do it on that page. Let's do it on another page. All right, so they are as follows. Or, oops, this is not the way. Okay. 1. A is row equivalent to In, right? So that's the one from section 2.2, actually. A has n pivot positions. Right? Well, if A row reduces to In, right? In has a pivot in every row and every column, right? So these two are obviously equivalent. If A row reduces to in, it means A has n pivot positions. If A has n pivot positions, then A row reduces to in. I mean, these are just two ways of saying the same thing. But again, these are things that we've all gone over already. Some of the equivalencies are less obvious than others, but here they are. The equation ax equal to 0 has a unique solution. Right, we've talked about that, about having a unique solution. Okay, either you have a unique solution or you have infinitely many solutions, if and only if you have, free variables. But you don't have free variables, you have n pivot positions, and A is an n by n matrix, so no free variables. Similarly, if this only has the unique solution, you have no free variables, so you have to have n pivot positions. So 2 is logically equivalent to 3. The columns of A are linearly independent. Right, well, we talked about that in the section on linear independence. You row reduce to echelon form or reduced row echelon form, and you see how many pivots you've got. And if you've got all the pivots you need, then the columns are linearly independent. But you do, right? So if the columns are linearly independent, you have to have n pivots. If you have n pivots, the columns are linearly independent. So these two are equivalent, and therefore this is equivalent to the other three. The linear transformation ax or tx t from Rn to Rn given by tx equals ax is 1-to-1. Right, well, in the section on section 1.9, when we talked about 1-to-1 and onto, right, the matrix transformation is 1-to-1 if and only if it has a pivot in every column. If you have n pivot positions and you have n columns, then you have to have a pivot in every column. Similarly, right? So these two are logically equivalent, 5 and 2, and therefore 5 is logically equivalent to the rest. The linear transformation, so just copy it. The linear transformation given by tx equal to ax is onto, right? Well, it's onto if and only if you have a pivot position in every row. But if A is n by n with n pivot positions, you have a pivot position in every row. So 6 is logically equivalent to 2, and therefore logically equivalent to the rest. Let's see. Yeah, the equation ax equal to b is either inconsistent, has a unique solution for each b in Rn. Well, in order for that to happen, you have to have a pivot position in every row, which you do, right? So it's logically equivalent to 2. there is a matrix B such that BA is equal to I. There's a one-sided inverse. There is a matrix C such that AC, this is IN, is equal to IN. So this is saying that you only have to check if the matrix has an inverse on one side. If it has an inverse on one side, then it has an inverse on both sides. Okay, this is a little bit different than all the other ones we've been talking about here, but it basically goes it basically goes as follows. So why is it that an inverse matrix need only be checked on one side? Okay. Well, if A times B is equal to I, if A times B is equal to IN, then consider the equation A x equal to 0. Actually, BA equal to IN. Consider the equation A times x equal to 0. Multiplying by B, we get that BAX is equal to B0. But this is equal to I. And B times 0 is equal to 0. And then I times x is equal to 0. Right? So, AX equal to 0 has only the trivial solution. X equal to 0. So the matrix A has n pivot positions. Right? So A inverse exists. Right? And actually A inverse will be equal to B. Right? Why? Well, if B times A is equal to IN, but IN is also equal to A inverse times A. Okay, well, A inverse works on both sides. So B, oops, I did this wrong. A inverse. So A inverse BA is equal to A inverse A inverse. So, well, wait a minute, I'm doing this wrong. Yeah, this is supposed to be A inverse A. So if BA is equal to IN, then A inverse A is also, well, A inverse A is also equal to IN. So BA and A inverse A are equal. Multiplying by A inverse on the left, right, this is equal to I. And this is equal to I. But anything times I is itself. All right, so there it is. So if you have a matrix multiplied on the left of A to give you the identity, then that matrix on the left has to be A inverse. for a matrix on the right, so here we looked at B times A equal to IN. If we have that A times B is equal to IN, then as in the previous paragraph, right, we switch the roles of A and B so that instead of B equaling A inverse, we have that A is equal to B inverse. So B times A is equal to B inverse is equal to I. Right? And actually, I don't need to do that. So that A equals B inverse. So now A inverse B inverse inverse is equal to, gives you that A inverse is equal to B. Okay, so if you have a matrix multiplied by A on the right, then it turns out that A is going to be equal to B inverse. So that means that B is going to be equal to A inverse. Okay, so that is the lecture for section 2.3.